Good morning, everyone. So, in today's class, we'll introduce the concept of cycle index. So, if you recall from the last class, we discussed the Burnside lemma, which helps us to compute the number of the equivalence classes. Now, in the Burnside lemma, you can see that it is computationally expensive to compute psi of pi because we need to identify all the colorings and then we have to see how many colorings remain fixed by the symmetry pi, which is not feasible even if we consider the case of polygon with 10 side or cube. Then it becomes very complicated. So that's why we will see a simpler technique which is known as cycle index to compute psi of pi. So we'll use the same formula, but we will see a technique to compute psi of pi. So for the computation, there are two important observations. The first one says that a coloring would remain fixed by pi if for each corner V, the color of C at pi is the same the color at pi of V. For example, let us consider 180 degree. Now this color is black, yes, and after 180 degree, this corner reaches here. Yes, so if this is also black, this is black, and after 180 degree this corner reaches here, which is also black, it means this is black, then the coloring remains unchanged. Similarly, if this is white, this should be white. Yes, so as I told you, pi 3 causes corners A and C to interchange and corner B and D to interchange. It follows that a coloring left fixed by pi 3 must have the same colors at the corners A and C, must have the same colors at the corner B and D. This we have already discussed. And since if we consider the two coloring of a square, then there are two choices for A and C, either black or white, or two choices for B and D. It means total 4 choices, and that's why psi of pi 3 is equal to 4. So this is one technique. Now if we have to simplify this technique, then we can recall the cycle associated with pi of 3. So pi of 3 can be written as AC and BD. Yes, so AC means this cycle needs two colors, which means A and C should have the same color, and this cycle needs two colors, so total 4 colors are required. So psi of pi 3 is equal to 4. So if we can write the cycles for a symmetry, then we can easily compute psi of pi for that symmetry. So second observation says that if pi I cyclically permutes a subset of corners, cyclically permutes, it means you can, this is cyclically permute, then those corners must all be having the same color. So this is the example. So now if we have to compute psi of pi, better is to get a cyclic representation for each symmetry and count the number of ways to assign a color to each cycle of corners. Yes. Now to further simplify it, let us classify the cycles by their length. So I say that if I write x1, it means I am talking of a cycle of length 1. x2 means cycle of length 2, or xj means cycle of length j. Yes. So this expression is known as the cycle structure representation. For example, for pi 3, this becomes x2 multiplied by x2, which is x2 square. So x2 square is the cycle structure representation of pi 3. Similarly, for pi 2, I write pi 2 as a, b, c, d. Therefore, it is a cycle of length 4, x4. Pi 3 I already discussed. Pi 1, there are 4 cycles of length 1, so x1 raised to the power 4. Yes. So now you can quickly try to write down the cyclic structure for each of these symmetries. So for this one, x1 raised to the power 4, pi 2 it's x4, pi 3 we already discussed, x2 square, then pi 4 comes, so pi 4 is again x4, 90 degree or 270 behave same. Then comes pi 5, so pi 5 is rotations, so there are two cycles, x2 square, pi 6 x2 square, pi 7 there are two cycles of length 1, which means x1 square, and one cycle of length 2. Similarly I can write for pi 8, so this is x4, this is x2 square, this is x4, and this is x1 raised to the power 4. So now if I add all of them, and divide by the number of the symmetry, then this is known as the cycle index. Yes, and now in the cycle index I replace each xi by the number of the colors. For example, if I am looking for 3 coloring, then I replace each xi by 3. In case of 2 coloring, I replace each xi by 2. And why it is happening? Because to compute psi of pi, what I did, 2 raised to the power number of cycles in pi. So for example, psi of pi 3 is 2 raised to the power 2 because it has 2 cycles of length 2. Psi of pi 1 is 2 raised to the power 4, 16. Yes, so if I compute psi of pi, it comes out to be this. And how it is happened? Because this one is x1 raised to the power 4 and I replace x1 by 2. This is pi 3, this is pi 2, this is simply x4, so I replace x4 by 2, this is again x4, and so on. Yes, so this is how you can see that it becomes very easy to compute psi of pi using the concept of cycle index. And now there is no problem. How many colorings are there? I simply have to, if there are k colorings, I simply have to replace each xi by k in the cycle index. So the idea is to first write the symmetry in terms of cycles, then compute the cycle structure, from there compute the cycle index, and then the number of the colorings. Okay, so now let's try the first question. So consider a necklace made up of 3 colors. Then how many different necklaces with 3 beads are there? Yes, so in terms of the necklace, we are just considering the rotation. So rotation means that psi of 0, so it is x1 cube, because there are 3 cycles of length 3, A, B, C. Yes, psi of 120 degree is A, B, C, and psi of 240 degree is A, C, B. So this is equal to x3, this is equal to x3. It means my cycle index is 2 times x3. Yes, and now if I am looking for 3 colorings, I replace each xi by 3. That gives me the required answer. So 1 by 3, 3 cube plus 2 multiplied by 3, this is equal to 11. Consider the next example. So consider it is made up with 3 colors with 8 beads are there. Now in case of the 8 beads, first I need to find the cyclic structure. So there are total 8 rotations are there. So those rotations are simply 0, 45. So I simply do 360 degree by n, or 360 degree, 8 sides are there, so by 8. So 0, 45, 90 and so on. Now for 0, there are 8 cycles of length 8. For 45 degree, you can see that A goes to B, B goes to C and so on. So it is x8. Now you can write down this cycle for 135 degree also. But if I just have to write down the cyclic structure, I know that it comes out to be cycle of length 8. So it is A goes to D, D goes to G, G goes to B, then E, H, C, F. Yes, so this is 45. 135 behaves in the same way, and similarly 225 and 315. Now in case of the 90-degree, you can see that A goes to C, then C goes to E, and E goes to G, and there is one more cycle of length 4. So total there are 2 cycles of length 4. Yes, in case of 180-degree, A goes to E, opposite. So you will get the 4 cycles B, F, D, H and C, G. So you will get 4 cycles of length 2. Yes. So 0, 90, 180 is covered. 90 is same as 270. So 270 is covered. And 360 is already covered. Similarly 45, 135, 225, 315 is covered. So now you can write down the cycle index. So cycle index is 1 by 8, then x1 raised to the power 8, then 45, 135, 225, 315, so 4x8, then 2 are 90 and 270, so 2x4 square and 1 is 180 degree. And now if m colors are there, I replace each xi by m. If there are 3 colors, I replace each xi by 3. That gives us the required answer. Okay. Let's try one more question. So now the total number of the colorings using pentagon. Now since it is not mentioned, I have to consider both the symmetries, rotation as well as reflection. Yes, 5 rotations are there. Rotations are quite easy. So 1, 2, 3, 4, 5. So for 0 degree, it is x1 raised to the power 5. And for all others rotations, you will observe that they all gives you a cycle of length 5. It means for the rotations, it is x1 raised to the power 5 plus 4 more rotation. Yes, this you can observe very easily. Now important thing is to observe the reflection. Now for the reflection, I fix one vertex at a time and consider the middle of the opposite vertex, and then I will do the reflection. So when you do the reflection, this one vertex remain fixed. So because of this, it is x1. In this case, 2 goes to 5, 5 goes to 2. So x2, 3 goes to 4, 4 goes to 3. So it is x1, x2 square. And since 5 vertices are there, so this is my cycle index divided by 10. Now in case of k colorings, replace each xi by k, and that gives you the required answer. Yes. One more interesting problem, number of different colorings of the vertices of following figure. So 8 vertices are there, but how do you identify the symmetry? Now for the symmetry, 0 degree is trivial. Now if you rotate it by 180, yes, 90 degree this structure would be changed. But when you rotate by 180 degree, you will get the same structure. Similarly, if you consider vertical and horizontal axis, reflection about vertical and horizontal axis, you will say you will get the same structure. So total 4 symmetries are there. Diagonal won't work because it is not a perfect square, so reflection about diagonal won't work. So 4 symmetries are there. Let's consider each one. So for 0 degree, 8 vertices are there, so x1 raised to the power 4. In case of 180 degree, you can see that this A goes to E, then B goes to F, then C goes to G, and D goes to H. If you rotate, So 90-degree rotation, you will get a structure like this. Yes, and then once you rotate again, you will get the same structure where A reaches to the opposite side. Now if you consider the vertical axis or horizontal, let's say first consider the horizontal axis. So when take the reflection, A and H got interchanged, BG got interchanged, CF got interchanged, DE. So horizontal. And if you consider the vertical, so this is the vertical. So in case of vertical, A reaches to D, H reaches to E, B, C and G, F. Now all three have the same contribution. There are 4 cycles of length 2. So yeah, 4 cycles of length 2. It means my cyclic index is as follows. Now let's consider the same example, but now you have to find the M colorings of the edges. Yes, now to find the colorings of the edges, you need to consider the edges. So you can redraw the figure by labeling the edges. So total 10 edges are there. Now symmetry won't change, 0, 180, vertical and horizontal. Try it by yourself. So for 0-degree, x1 raised to the power 10. Now let's say vertical if I consider. So this is my vertical. So now I have to see the colorings of the edges. So when I see the vertical, then you can see that this G reaches to J, A reaches to C, D reaches to F and H reaches to I. But B and E remains as it is. There is no change in B and E. Those edges would remain at the same position. Yes. If you consider the horizontal axis, something like this, then A and D, then B, E and C, F got interchanged, but the 4 vertical edges remains at the same position. They don't get interchanged. And 180-degree rotation, in case of 180-degree rotation, all the edges, so A would reach to F, B reaches to E, C would goes to D, H would goes to I and G would go to J. So now you can see the observation. This is x1 square and x2 raised to the power 4. This is x1 raised to the power 4 and x2 cube, and this is x2 raised to the power 5. So add them and divide by 10 gives you the required cycle index, and from there you can compute the M colorings. So let's discuss the last question, which says that determine the number of 3 colorings of the 4 corners of a tetrahedron. So tetrahedron, we are moving to 3D now. While considering only rotation, we are not considering the reflection. Now to visualize it, there are 2 videos, because there are mainly 2 type of the symmetry. One is, let's say this is the tetrahedron. So you fix one point, and let's say these are ABC. So you fixed one point and rotate it by 120 degree and 240 degree. So in that case, the position of this triangle would change. So 2 symmetries are there, 120, 240 for one particular vertex. 4 vertices are there, so 4 multiplied by 2, 8 symmetries are there. Yes. Now identity would be unique. So 0 degree would be, so 8 plus 1, 9. And one which is visible from the video, what you do is that you consider the 2 opposite edges and rotate it by 180 degree. If you do that rotation by 180 degree, then again you will get the same tetrahedron. Yes, but please do observe in the video. So since 2 opposite edges you are considering, total 6 edges are there. So you consider two edges at a time, so 3 symmetry would come because of 180-degree rotation. So total 12 symmetries are there. Yes, so this is what I was telling. You fix one point and rotate it, so this triangle would get interchanged, 120-degree, 240-degree. So the contribution would be x1, x3, and 8 symmetries are there, so 8x1, x3. For 0-degree it's already 4 vertices are there, so x1 raised to the power 4. And this is how 180-degree would work. In that case 1 and 4 get interchanged and 2 and 3 would interchange, so x2 square, and 3 symmetries are there because 3 opposite sides are there. So if you consider all of them, then your cyclic index would be 1 by 12 x1 raised to the power 4 plus 8 x1 x3 plus 3 x2 square, and 3 colorings are required, so you will have the required answer. So that's all from today's class. Thank you very much.